Right. Now we've been through some properties for logarithms, getting familiar, right? I feel like we, we're buddies now. We're pals with the logs. Let's see if we can do a graph for what sort of a generic version of these would look like. And I said generic, but I really didn't mean generic. Let's actually start with the very particular. Let's do f of x is log base 2 of x. And what we're going to do as we go through this is we're going to at least sort of mentally compare this to f of x equals the exponential function 2 to the x. We'll do our usual thing. Let's make a table first. We'll see if we can figure out what some of these like patterns are, and then we'll go from there. I have to set this up just a little bit. If we do sort of exclusively random numbers, we're going to sort of run into some issues. So I'm going to be a little bit particular with what I pick for our x values. I'll sort of explain these choices as we go. Let's do x is 8. Let's do x is 4. Let's do x is 2. Let's do x is 1. Let's do x is 1/2, 1/4, and 1/8. You can probably start to see a little bit of a pattern here, right? What do all these x values have in common? Well, they're all powers of 2, right? So the idea with a logarithm is, we're putting things in for x that should be kind of quote-unquote easily achievable with 2 as a base, right? The log value itself is whatever the exponent is. So we're trying to think of, okay, 2 to the question mark would kind of give us this x value. So how do I get from 2 to 8, 4 to 1, right? And then kind of 1/2, 1/4, 1/8. In particular, you'll note that I'm not trying to do x equals 0, and I'm not trying to do x equals any sort of negative numbers. We don't have a way, if 2 is the base value, we don't have a way to get from 2 to 0, right? 2 raised to the 0 is 1. We can't get from 2 to 0 itself. We can't get from positive 2 to any of our sort of negative numbers. It's just not possible. So the only really x values we can use here are going to be positive values. We'll sort of identify and talk a little bit about the domain generically once we're at the end. So let's find all these values, and then we'll make a sketch. So this is going to be, right, f of 8. So this is log base 2 of 8. How do I get from 2 to 8? Well, it must be that 2 cubed is 8, right? So then that value is going to be 3. So that's y value 3. F of 4. How do I get, right, log base 2 of 4? How do I get from 2 to 4? 2 raised to the 2 is 4, right? 2 squared is 4. So the y value here is going to be 2, right? The y values are syncing up with the exponents. F of 2. How do I get from base 2 to 2? How do I not go anywhere at all? Well, 2 to the 1 is 2. So then the value here, right, the exponent is 1. Go a little faster. How do I get from log base 2 to 1, right? 2 to the 0 is 1. So then this must be 0. How do I get from log base 2 to 1/2? How do I get from 2 to 1/2? So the answer is the exponent is -1, right? Do a reciprocal. You can probably guess what's going to happen as we get to 1/4 and 1/8. I hear you yelling at the screen. 2 raised to the -2 is 1/4, right? So flipping it and squaring it. So that's going to be -2, and then our last version we expect will be -3. This should check out, right? How do I get from 2 to 1/8? I got to flip it and cube it. So -3. So this is the kind of table that I get. What would this look like if I actually sort of graphed it out? We'll do a rough sketch. This is not going to be perfect. And we'll notice that sort of one of the things here that's happening, we're sort of hitting both positive and negative y values. The one thing we're not really hitting is we're not really hitting any negative x values. So I'm going to sort of sort of lean towards the positive side here. So 1, 2, 3, and x. One thing to note right there, x values actually get pretty big pretty fast, right? 1, 2, 4, we have to go all the way out to 8. This one's just kind of not going to fit directly on here unless I really extend this over, which honestly would look a little bit strange. The y values going between 1 and 3. And one of the things here you're going to notice that will sort of make more clear as we go is we're really getting, if you look at this table versus the table we did for 2 to the x, these tables are essentially the same x and y values, they're just the roles are reversed, right? So this x column is sort of what we had in the y column for 2 to the x, and the y column is what we had in the x column for 2 to the x. So we flip the roles of x and y. Again, sort of emphasizing that these two functions are inverse functions to each other. We're sort of reversing the roles of the x and y values. So what are our actual points? Let's start at this 1, 0. Logarithms, right, in general, will tend to have this value. So x is 1 and the y is 0. This is, right, the sort of inverse version of what we had in our exponential graphs, which was the x is 0 and the y is 1, right? The 0, 1, anything raised to the 0 is 1. That role is reversed. Let's do the easy ones here. So x is 2 and the y value is 1. X is 4 and the y value is 2. Right, our kind of 8 and 3. Kind of eyeball it. It's maybe somewhere out there. To fit these other ones on, right, x is 1/2, 1/4, 1/8. 1/2 we can graph pretty reasonably. 1/4 gets a little tighter, gets a little tighter. And so what's happening here is we get, instead of a horizontal asymptote, we're getting a vertical asymptote. X is 0. Where was this? I'm trying to shoot for this guy over here. Right? So we have vertical asymptote at x equals 0. We're heading down towards negative infinity. You could imagine as the x values get, right, 1/16, 1/32, yada, 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 bigger and bigger and bigger, or I guess in some sense smaller and smaller and smaller, closer to 0, the y values get to be bigger and bigger negative numbers. You're sort of flipping the two and raising it to a bigger and bigger value. This is sort of looks like, what would be kind of a sideways exponential growth. What that means for us is that it's increasing. It's just increasing kind of slowly, if we're being honest, right? This gets to look sort of more and more horizontal. It technically gets bigger and bigger and bigger. It just, you need to take a bigger and a bigger step to the right to sort of go up by 1 unit. The further out you go, you have to go sort of further and further and further to make any sort of vertical progress. You do make vertical progress. That does happen. It just takes a long time. If I graph this and I compare it to if we do a g of x is like 2 to the x, what kind of coordinates did we have there? Well, we had, 0, 1, we had kind of 1, 2, 2 would be up at 4, and then these guys were sort of dropping down. So an exponential version is going to have a very similar shape, but it's twisted and headed the other way. It's sort of flipped on a diagonal type axis. So this for us was y is log base 2 of x, and our y graph, our red graph is 2 raised to the x. So the logarithm and the exponential with the same base have this inverse relationship. They're sort of complementary graphs. They do similar things, but they're sort of headed in different directions. The roles of the x's and the y values are reversed. You're going to have a similar kind of relationship if you do log base 3 versus 3 to the x, the natural log versus e to the x. All of them will have this same kind of relationship. and these same kind of connections. If we want to, a couple different like properties. So like log base 2 to the x, right? So our domain here, right, the x's, they're going to start at 0, but we don't include 0. We go out as far as we want to the right, so anywhere from 0 to positive infinity. The range is really going to be all real numbers. This negative one obviously drops very fast. We're going to hit all the negatives, and in theory we're also going to hit all the positives. It just happens really, really slowly. If we kind of compare that to the properties for 2 raised to the x. Oh, I color coded that bad. Let me make this one blue instead. 2 raised to the x. That looks kind of blue. So the exponential, right, the domain is all real numbers. The domain could be any kind of x, negative infinity to positive infinity, but now the range is where we're limited, right? We never hit 0. We're exclusively in the positive, so kind of starting at 0 but not including it and sort of moving up. So you can see we get this kind of complementary relationship between these two functions. The domains and the ranges kind of flip back and forth because what's happening here is the role of the x values and the y values are flipping back and forth. It's similar kind of things that are happening, but we're changing the roles of the x's and the y's. So our exponentials and our logarithms are inverse functions. The graphs have this sort of flipping the roles of the x's and the y's. If we make tables, right, the tables as far as the x and the y like columns go will have sort of flipped values. You get the same kind of like correspondences, but the roles will reverse from one to the other, and that's going to be true sort of regardless of the base. I'll say, but I guess not necessarily graph, if we used a logarithm with a fraction base, a base that was somewhere between 0 and 1, we'd get a different facing graph. We'd get a slightly different relationship happening in the same way that we do with our sort of exponentials. I'm a little bit out of space to graph it, and we honestly won't see those tons and tons. But in theory, right, this sort of generic log graph is for base values that are greater than 1. If your logarithm base is between 0 and 1, you're going to get a slightly different curve in the same way that you get a slightly different curve for our exponential graph. That's the basics. That's it for 4.2. See you in the next video.